Alright, so we're starting today's topic, or today's video off with something, I'm sure. Gotta wait for my thing to load. We're starting off with some lemmas on commutators. I'm gonna write that out here. Lemmas on some commutators. And here we're working, sorry, 1 sec. So here we're working in the general case. So since for each alpha in our basis, the standard basis for the three-dimensional simple algebra S alpha may be taken to be part of the chosen Chevalier basis for L, we can apply our results from the last video to situations involving only a single root. So now we want to look at how to deal with linearly independent pairs of roots. So start things off with the lemma. And the first lemma here states we're going to have V and W as L modules with they call them subgroups A and B. If A and B are invariant under all endomorphisms of the form x alpha t over t factorial, for alpha a root in phi and t a positive integer, of course, then so is a tensor B inside of the tensor W is also invariant under all of them, is what this is saying. And so the proof. Recall that the action of an element XA on V tensor W is, we essentially expanded out like our tensor is the Lie bracket, and this is a derivation. So XA acts on V, and that is the result being tensored with W, plus V tensored with the action of X alpha on W. Now, from the binomial expansion, we get that x alpha to the t over t factorial of V tensor W is the sum for k from 0 to t of x alpha to the t over k factorial acting on V tensored with, and this is our k, because this is just a binomial, right? So x to the x alpha to the t minus k. The rest of the x's, of course, over t minus k factorial are going to be acting on W. And if, of course, if V is in A, W in B, the right hand side is in A tensor B. Alright, this comes with a corollary. We're going to let LZ, or of course, recall this is the integer span of the Chevalier basis chosen for L. And then for alpha, a root alpha, and a positive integer t, the adjoint of x alpha to the t over t factorial leaves Lz tensored with itself enough times invariant. And this is immediate from our previous lemma. So we now have a subset C of phi is called closed if alpha and beta being in C and with their sum being a root implies, so keep in mind, both alpha and beta have to be roots themselves, as C is a subset of our root system. So that just makes their sum also a root. So it's essentially just a subset of the roots that's closed under addition in the way that you would expect of a subset of the root system. An example. For phi, some examples of a root system would be all phi, the positive roots of phi, and the set of all I alpha plus j beta in phi for I and j positive and alpha beta in phi. They say they have to be linearly independent, but I think wouldn't it still work even if they're not? Because like it just has to be closed under addition essentially. And if it's just the z span of the, it's just the positive z span of the one root, then it should be closed under addition already, right? I mean, it'll just be the positive, just be the one root anyways. That brings us to a second lemma. We're going to say let C be a closed set of roots with no negatives, essentially. We're going to we're going to use our fancy x here. That's not even an x. Be the subring of the universal algebra of L with one generated by all x alpha to the t over t factorial for alpha in our closed set and t being a positive integer. Then relative to any fixed ordering of our system, the set of products in the given order for x alpha to the t alpha over t alpha factorial forms the basis for the integer module x. Now the proof. we know the f-span of the LA for A being in our set is a subalgebra. We'll call it normal X of L. And by Poincaré-Berkoff-Witt on the universal algebra of L of X, sorry. The products suggested above form a basis. For our fancy X over F. So we show the coefficients lie in the integers. So we're going to call the sum of T alpha over alpha sum of T alpha for alpha in our closed subset, the degree of this product of x alpha to the T alpha over T alpha factorial. If x in X is non-scalar, X is C times the product of X alpha to the T alpha over T alpha factorial plus terms of plus higher degree terms. Where C is non-zero and the remaining terms of degree T as the sum of T alpha involve sequences distinct from our set of T with T alpha. And our fancy X acts via the adjoint representation on L tensored with itself to T copies. In particular, we're going to look at X times the tensor of T alpha copies of X minus alpha tensored with T beta copies of X minus beta, and so on, where these are our terms in our positive C, in our closed subset C. Now, the question is, we want the component of this element in H tensor with itself enough times relative to the standard Poincare Birkhoff width. The first term in X, which is the product. Sorry, 1 second. Things are always happening. Which is the product of A copies of X to the alpha to the T alpha over T alpha factorial yields C times H alpha tensored with itself yields C of our above term, which is, well, actually this time it's going to be T alpha tensors of H alpha tensored with T beta terms of H beta tensored with so on throughout our C, and all other terms which we write as X alpha is to say U alpha over U alpha factorial yield no non-zero component in H tensor with itself. Either there's too few factors, as in the sum of the U alphas is less than the sum of the T alphas, or they're distributed wrong. Now, by our previous corollary, X preserves the T tensor of T copies of L of Z. With okay, alright, this is new thing. We also may assume that alpha, which is the first element in our ordering of C, is simple as LZ is independent of our base. The H beta for beta being our simple terms in C form a basis. I didn't mean to do that, sorry. That happened in the last video too, didn't it? These form a basis for the free module, for the free integer module HZ, which is L of Z tensored with H. So there are various tensor products form a basis for the free integer module which is a bunch of tensor copies of hz as needed. As our C of the tensor of TA of HA and so on lies within this HZ tensor enough copies with HZ, C must be an integer. Now, the term, which we can write on a new page, our term of C times the product of X alpha to the tensor alpha over T alpha factorial may be subtracted and the argument repeated. So we are done by induction on a number of terms. Now we are going to call any product of X alpha T over T factorials and some Hi minus J over K. Choose K. This I is supposed to be a subscript, but it's hard to tell because of the how cramped it is. In the universal enveloping algebra of L, a monomial of height being the sum of the various t's occurring. This brings us to our next lemma. Our third lemma for this section, which goes, we're going to let alpha and beta be roots. We're going to let km be positive integers. Then xm beta over m factorial. Ooh, let me write this better. X beta to the m to the m over m factorial times x alpha to the k over k factorial is an integer linear combination of x to the k alpha, x alpha to the k over k factorial, x beta to the m over m factorial, and other monomials of height less than k plus m. If alpha is a copy of beta, we are done. Plus or minus beta. Otherwise, apply the previous lemma to the set of roots of the form I times alpha plus j times beta to write the, of course, I and j being positive, to write the given monomial as an integer linear combination of x I alpha to the k over k factorial times x beta to the m over m factorial and other monomials. Now we still need to show that they have smaller height, which they have a smaller height by Poincare-Bertikoff-Witt, and since we're using a potentially scalar multiple of a Poincare-Bertikoff-Witt basis, we are done. And from there, we can go immediately into another lemma, which states this time, so we're going to have lemma. Let alpha and beta be in our root system. Ft be a polynomial and over t, where t is of course an indeterminate. Then for all positive integers k, x alpha to the k times f of h of beta is f of h of beta minus k times alpha of h beta times xk to the alpha. And the proof for lemma number 4 here. And by linearity, we can assume that f be of the form t to the m. So then our assertion becomes saying that x alpha to the k times f of h beta, which is h beta to the m, is f of this thing inside, which our thing inside is h beta, minus k times alpha of h beta. And this is being applied f to it, so in our case this is assumed by linearity to be the power of m, and this is going to be x alpha k. If k or m equals 0, then of course this is going to be, we are done. If k and m are 1 as a base case, we have this formula becomes, well, x alpha times h beta equals h beta, and then we're going to distribute this x alpha inside, so h beta x alpha minus k, no, k is 1, so that's just going to be alpha of h beta times our x alpha, which is, yeah, which is our h beta minus alpha h beta times x alpha. Now, so by induction, by induction proceed on K and M. So we see for fixed K our equation can be in our equation, I'm going to try to fix this messily. In our equation we can increase M directly, just straightforward from manipulation of this equation. So it holds, so our equation holds for K equals 1 arbitrary, M arbitrary. We can likewise, this is kind of a non-proof, but we can likewise expand our K. And you can tell I'm going a bit slow here because I know we're probably a little bit under time here. Yeah, it's been like half an hour, but oh, you know what we can do? The next section is going to be short. That'll set us nice up for tomorrow, next video. So let's go ahead and do that here. This is proof of kostant's theorem. So we're going to fix, at the start, we're going to fix an ordering, say alpha 1 through alpha m of our positive roots. This is denote m, or alternatively L tuples of non-negative integers by capital A being A1 through AM, B being B1 through BL, and C being C1 through CM. Now I'm going to define elements. The universal algebra of L as follows. F of our A is going to be the product from 1 to m of x negative alpha I to the AI over AI factorial h of beta is going to be the product from 1 to L of our hi with its associated, choosing our associated bi, and E of C is going to be our product of from 1 to m of x to the alpha I over to the ci over our ci factorial. Note that Note that the various possibilities for HB form a basis over F for the universal enveloping algebra of H. We saw this before, and with joining this with the Poincare-Berkhoff-Witt theorem, we show that the various elements FA, HB, and EC form an F basis of the universal enveloping algebra of L. This brings us on to Kostant's theorem. So we're going to let ULZ be the subring of UL with one generated by all x alpha to the t over t factorial, where alpha is a root, t is a positive integer, as you've seen. Let me try to write this better. I'm going to let B, try to write this fancy here, be the lattice in the universal enveloping algebra of L with an integer basis of all FA, HB, EC. Then B is our ULZ. And the proof. So, first of all, we know that each HI choose BI lies within ULZ. So our fancy B lies within UL of Z. Now the reverse direction is the tricky part. We're going to we can reduce our case down to our monomials, and we're going to use induction on the height of our monomials. Height 0 monomials involve only factors of the form h sub I minus j choose k and lie in our B by previous proposition. In general, our last few lemmas let us write a monomial as as a integer linear combination of other monomials for which factors with x negative alphas, h is, and x alphas in the prescribed order. The identity that t to the k over k factorial t to the m, times t to the m over m factorial is equal to m plus k, choose m, t to the k plus m over k plus m factorial ensures each x plus minus alpha will appear in at most one term, not and. One term of each resulting monomial. And so we are done by our previous lemmas. And from that, I think now we can call it here for our video comfortably. Next time we're going on to admissible lattices. So I think we're getting near the end, I think there'll only be a couple more days, and then we'll be on to Lie groups, which is exciting, kind of scary. My professor told me that the Lie group sections weren't as good, so maybe it might be a disappointment. But anyways, I'm glad to be getting through the books here. Thanks for watching.